Good morning. Yeah, good morning. Assalamu alaikum. Yeah, I will start now. So this is the second lecture for this chapter. So I'll go back to the contents and see what we have done so far. In section 1, we define the electric current. How many of you remember the definition of electric current, the formula? Please respond. Abdullah, what is an electric current? How did we define it? Guys, this is what I've been telling you all along. You should be paying attention in the class. You know, this is a simple thing. Yeah, thank you, Haya. Thank you very much. So we define the, Haya, send me the chat box. It is Q over T. Well, it is the flow of charges, right? That is what electric current, the rate of flow of charges. So you charge divide by the time. Okay, so like acceleration is rate of change of velocity, like that. Current is the rate of flow of charges. We take a perpendicular area to the flow of current and see how many charges are crossing that area and the rate at which it is crossing. I mean, divide by the time, per unit time, it gives us the electric current. Okay, then we looked at the current and the drift speed of the electron, and we got a formula again between the current and the drift speed. Then we talked about measuring voltage and current in a circuit. We used a device. Okay, let me ask another question. What do you call the device that measures the current? Haya, what do you call the device? Somebody please speak in the mic so if we need to know that everyone is participating rather than the chat box. Haya, can you tell me? What do you call the device that measures the current? Ammeter. Yeah, Mashal, good. Okay, yeah, ammeter is measuring the current. So what do you call the device that measures the voltage? Mashal. Please speak into the mic. Okay, so let's all participate here. Okay, I don't want to be just talking to myself here. I'm the only one in the classroom. I'm in the classroom. Please. Voltmeter. Thank you, Maha. Thank you very much, Maha. Yeah, fine. So then, you know, we introduced the resistance, resistivity, and the Ohm's law. Okay, Ohm's law is actually the definition of the resistance, but for certain material, the proportionality constant, the relationship between voltage and the current, we have a proportionality constant, that is the resistance, it stays constant. So we call such devices as ohmic devices, and we can say it obeys Ohm's law. Okay, it's not necessarily a law, it doesn't apply to all materials. Okay, so you can take it as the definition of resistance. Then we introduced resistivity. That's where we stopped. Now we are in section 5. Let me go there. So we did this question, then here we are. Section 5. Now we looked at the resistivity. Resistivity, it is a property that is constant for a given material. Say, for example, copper material, it's a metal. It will have a certain resistivity. So low resistivity mean good conductor. So metals are good conductors, so we'll have a low resistivity. But another metal, say aluminum, for example, will have a different resistivity. Higher than the copper because less of a conductor compared to copper. For most metal, the resistivity increases with increasing temperature. So what happened at higher temperature, the atoms inside the metal, they vibrate, the constituent atoms, with increasing amplitude. Okay, they are fixed in place, but with temperature, they can start vibrating with the increasing amplitude as you increase the temperature. So then the electrons, which are the charge carriers, the mobile charge carriers in a conductor, metallic conductor, they find it difficult to pass through the atom, so resulting in a higher resistivity. So resistivity is a measure of how easily or how difficult for a charge to flow through the material. Okay. So we got an equation here, how the resistivity varies with the temperature. In a limited temperature range, so we can see it is linear. So here, resistivity, the rho, this is the resistivity, it is proportional to the temperature. So the resistivity is proportional to the temperature, and the other things are all constant here. This is the resistivity at the temperature, say at a reference temperature T0, and alpha is a constant, and it is called the temperature coefficient of resistivity. Okay, so we are introducing another formula here, how the resistivity varies with temperature. And usually these are a reference temperature and the resistivity at that reference temperature. Usually we take the reference temperature to be 20 degrees. Not necessarily it has to be 20 degrees, but that is the standard. All right. Now, we can also look at how resistance, not the resistivity. So you know they are two different things. So we can also write for the resistance a similar equation as we had for resistivity, because there's a relationship between this R and resistance and resistivity. This is the relationship which we learned when we define the resistivity. So provided we have a given substance, given material, a given piece of resistance, okay, if the cross section is constant and given mean a certain length of the piece of resistance, the resistivity is proportional to the resistance. So it's a matter of, we can just say if resistivity varies with temperature linearly like that, resistance will have a exact same relationship with the temperature. Same coefficient of temperature coefficient of resistance. Alpha is called the temperature coefficient of resistivity. Okay, is that all clear? Please give me some feedback, please. I need to know that you are listening and there is no problem. Okay, very clear. Thank you very much, Maha. Now we come to the next section. We are going to almost finish this, okay, maybe early. Then we can take some questions from the midterm exam and do, okay? So that kind of review for you. Electrical energy in a circuit. Now, in a circuit, when the charges move through the battery in a circuit, we have a battery. The battery will give the energy to the charger, so it will, increase its potential. So the potential energy of the system is increased by this amount, because if there is a potential difference of delta V, the change in the potential energy will be, well, instead of Q, I'm going to call it delta Q, the amount of charge that is being pushed out. Where is it getting the energy from? From the chemical potential energy inside the battery. So that is when, so those chemical potential energy inside the battery decreases and it comes as an electrical energy that is supplied to the circuit. Then as the charge moves through the resistor, there will be resistance in the circuit. it loses this potential energy during collisions with atoms in the resistor. So it will make the temperature of the resistor to go up. Okay. Right, so let's take a circuit now and see what's happened. What happens, a simple circuit. We got a battery and just a resistance. Okay, it could be the resistance inside the bulb or some other appliance, doesn't matter. So we'll just take a simple, just a battery and a piece of resistance. So, and to explain this, okay, the battery has this negative terminal here and the positive terminal here, probably say 9 volt something. So I'm going to put some points A and B, and I'm going to ground this point A, which is connected to the negative terminal of the battery. So we are effectively making the potential at point A at the negative end of the terminal to be the same potential, electric potentials as the earth or the ground. So we usually take that to be arbitrarily 0, the ground potential. So if that is 0, the potential at B or the positive end will be 9 volt. The potential difference between or the voltage of the battery is 9 volt. Okay, that's the difference. But we can arbitrarily make this point A to be 0, the negative end to have the absolute potential of 0. Well, when we connect it to the ground, we usually take the ground potential to be 0. Then the positive terminal, we can say, has a potential of 9 volt. So now imagine a certain amount of charge, say delta Q, is moving around the circuit from point A and come back to point A because it's a circuit. It just flows in this circuit. Okay. Now let's see what happened in the process. Okay, we are again saying the point A is the reference point. It is grounded and its potential is taken to be 0. Now, as the charge moves through the battery from point A to B, the potential energy of the system increases by delta Q delta V, because inside the battery, so the chemical potential energy will give the energy, it will transfer to the electrical energy of the charges. So as it goes from A to B, the charges will acquire energy, okay, corresponding to the 9 volt, and it will increase by the amount delta Q. If that is the amount that is passing from A to B, the potential will be increased by an amount delta Q into delta V. That is the potential energy change. Potential energy change is equal to Q into potential change, potential difference. That is how we define the potential in terms of the potential energy. Then what happened? As it goes through, then it moved through the resistance. So it goes through C to D. We are talking about a positive charge that is moving. So when it goes through C to D, that gained energy will be lost as it moves through the resistance R. Okay. As the charge moves through the resistor from C to D, it loses energy in collision with the atoms of the resistor. This energy transferred to internal energy of the resistor. When the charge returns to A, that is the negative terminal of the battery, we can say the net result is some chemical energy of the battery has been delivered to the resistor and caused its temperature to rise. So as the internal energy of that resistor. So that we covered one more section that is on the electrical energy. Now we talk about electrical energy and power. No, it's still in the same section. Okay, so power is also associated with the energy. Now, what is power? This is not something new. We already know what power means. Can someone tell me what is a power? What is the relationship between power and energy? Noor? I need to ask you time to time because I don't have anybody sitting in front of me. So the online people should be active, please. Noor, could you tell me what is connection between power and energy? Yeah, Maha. Thank you, Maha. Power is the rate at which energy is transferred, right? That is what power. This is not something new, okay? We learned about this even in this, chapter 17, chapter 16, I mentioned it, okay? So power is how fast the energy is transferred. Maha, yeah, Haya. Power is not watt. The measurement, SI unit for measuring power is watt, okay? But what is power? Power is the rate at which the energy is transferred. So here, the rate at which energy is lost to the resistor, which will be energy. Energy is transferred is delta Q delta V divided by the time. So that will be the power. So now we can see this is current. So you can see the power is current multiplied by the voltage or the potential
Delta
difference.
V.
Right. Yes. Delta V. Yeah. Yeah. Is there a question? I heard something. I didn't notice who it was. You have a question,
No, I
please
just
ask
answered.
again. Oh, okay. Thank you. Thank you. All right. So the power we can see in electrical circuit, we get the expression it is equal to current into voltage or the potential difference. Potential difference is also, called the voltage. So volt difference, voltage simply. So that's another equation that you have to know, a basic equation. Then again, this we had the power for in chapter 17 or 16. Now I remember for the capacitors, right? For the power in a capacitor, we had this expression half Q delta V. Then for the energy stored, not the power, the energy stored in the capacitor, we had an expression. Then here, this is the power. Okay, the power in a circuit will be power delivered in energy lost in is the power. It will be current through that resistor, if that is a resistor we are talking about, into the potential difference across that element. Now we also know that we have these things obeys Ohm's law. Ohm's law is, can you tell me what is Ohm's law? Okay, it is time for you to respond again. What is Ohm's law?
I equal
I is equal to. Rather, tell me in terms of that's the
Q
definition of
over
R.
delta
R.
T.
No, no, no. I'm not talking about I. I'm asking you the Ohm's law. What is Ohm's law? That relates the, I
Resist.
already wrote it. Resistance is potential difference divided by the current. Okay, now I can use this into this expression for the power. Then I can also show you the power can be written as not just I delta V. Starting from that, I can also show by eliminating the potential difference from that equation, Ohm's law equation. I can say power is also equal to I squared over R. By eliminating current, again from the Ohm's law, I can also show the power is equal to delta V squared over R. Okay, now come to the unit. What about the unit? Unit is what? Power is energy divided by time. So that means energy is in joule. Joule is the SI unit for energy.
Joule per second.
And time is second. So it's joule per second, right? So joule per second, we have a one name for joule per second, which is watt. Okay. Okay, here we are. So the SI unit for power is watt, okay, which we just discussed. Okay, anyway, I and delta V has to be in SI unit. I must be in amperes. R must be in ohms. Suppose we are using the other equation, and delta V must be in volts. The unit of energy used by electric companies. Yeah, now coming to the energy, I'm back to the energy. I can write if power is equal to energy divided by time, I can say energy is the power multiplied by time. So I can also say the energy unit joule is watt second. So instead of saying watt is equal to joule per second, I can write it this way as well. As the, you give the subject, make the subject to be the energy. So joule, that is the unit for measuring energy, can be said as equal to power into time, that is watt second. But however, this energy, SI unit joule, 1 joule is a very, very, very small quantity. 1 joule is a very small quantity. If if your electricity board, say uh, Saudi electricity board, they want to charge you for your energy consumption. They don't charge for the power and how much joule you used. Okay, they want to charge for energy consumption, and say suppose you use 1 joule. The price of 1 joule is very small quantity. If you want to charge for 1 joule, maybe the price will be like 0.00001 halala. Okay, just very negligible, small amount of energy. So that's why it is practical to define another energy unit called the kilowatt hour. See, 1 joule is 1 watt second, right? If you use an appliance with 1 watt power for 1 second, that will be 1 joule. Appliance which draw the energy at the rate of 1 joule per second, and you use it for 1 second, then the energy you consume is 1 joule. This is very, very small, minute amount of energy. So you cannot, practical unit, if the electricity board want to charge you, is kilowatt hour. So now you can see what is 1 kilowatt hour is equal to kilowatt hour. So we need to convert it into watt second, right? So kilowatt mean 10 to the power 3 watt. An hour mean how many seconds in an hour? How do you get that? 1 hour is
60 by 60.
60
Tata,
seconds, right? 60 minute. And again 60 minute to make the minute in
360.
3,600. Yeah, okay. 3,600. Yeah, let me, so 3,600 second, 1 hour is. So that you can see, that mean 1 kilowatt hour is equal to 1 into 10 to the power 6 watt second or joule. Watt second mean joule. Not 1, 3.6. Here it is. So you can see 3.6 million joule is the practical unit for the electricity board to charge you for energy consumption. So a huge million joule, okay, 3.6 million joule, then maybe it probably 1 halala or something, okay? So that is why we are defining this new unit for measuring the energy. It's not SI unit, okay, based on the SI unit. So, but it is more practical unit for charging for usage. Right, so we now come to the next section, the last section in this, chapter 17, superconductors. You must have heard of superconductors. You know, what is superconductor? It's a class of materials and compounds. So now, you know, you can make compounds, superconductors out of compounds, mixture of different elements whose resistances falls to virtually zero below a certain temperature. It was discovered, you know, way back, I can't remember exact, for helium, very, very low temperature. You are talking about something very close to the absolute zero. You know, absolute zero is minus 273 Kelvin, right? So 0 Kelvin is the absolute zero. So we have somewhere around 4 Kelvin. They discovered in the 1900s, somewhere in the early 19th century or even before, exhibit this zero resistance. Conductors, normal conductors still have resistance, small, but it will have some resistance. But this class of superconductors called, it comes to zero, ideal, just no resistance at all. But it happens, they observe very low temperature, something like 4 Kelvin. Below that, it becomes a superconductor. But later, in 1986, it was a breakthrough. Yeah, well, we will first discuss this. Okay, superconductor. Then we call this temperature at which material become a superconductor as the critical temperature, TC, critical temperature. Because if there is resistance, the energy will be lost because it will turn into temperature, thermal energy. Okay, thermal energy cannot be get back; it is lost. So that's why, okay, it is get wasted. Cannot become a useful energy if when it is thermal energy. Now, this happens, very low temperature. We call this critical temperature, below which it becomes a superconductor. So we have a graph here that shows from some metal what happens at that temperature. It sharply drops to zero resistance. The value of this critical temperature is sensitive to composition, chemical composition. We can make different amount of different elements and get a compound which has a higher TC, critical temperature. Pressure, if we increase the pressure in which that material is to a high pressure, then you can increase the TC, the critical temperature at which it becomes a superconductor. The crystalline structure also, certain structure will become inducive to being a superconductor. Okay, now once a current is set up in a superconductor, it will be there forever. You don't need a battery because battery is needed to drive the current around. Okay, that is because there is a resistance in the material. So if you want to get the current flowing, we need to supply energy. But if there is no resistance at all, like in a superconductor, then there it is. Once you have the current, that current will persist forever without any applied voltage. That is super. I mean, you can imagine the possibilities. Okay, now that is why people got excited. So 1911 was when it was discovered, and for very low temperature like 4 Kelvin. And 1986, it became a big topic because they found high temperatures of superconductivity, but it is only 30 Kelvin. It is very, very cold, okay? But it's much higher than, it is above the zero, not 4 Kelvin. So people get very excited, they thought, okay, if we can get a room temperature superconductor, that will be a dream come true. I mean, they can do so many things because there are no resistance, it becomes super efficient. 1987, the next year, they got even higher temperatures, critical temperature for, yeah. Then currently, they say 150, practical 150 Kelvin, not centigrade, okay? Still it is minus, but it is above, above something like liquid nitrogen temperature, well, around liquid nitrogen. But actually, last year, they found they discovered the first high temperature superconductor, uh, room temperature superconductor. Well, not exactly 25 degrees, but 14 degrees Celsius. That is, as good as room temperature. Okay, and in some places in the cold countries, the temperature can be 14 degrees and people, comfortable in that temperature. So that is another breakthrough. I think it is 2020 in October. And then there are more materials that are superconductors and more applications also come out. Here, there is one interesting phenomena is demonstrated here with superconductors. What we have here down is a superconductor in liquid nitrogen because the critical temperature is very low. So it is, but it is above the liquid nitrogen has a temperature of 190 Kelvin, that is minus 190 degrees. No, I'm sorry, 190 Kelvin, that is minus 77 degrees. Okay, very cold. But anyway, there are superconductors which become superconductors at this liquid nitrogen temperature. So we keep this in a liquid nitrogen and we bring a permanent magnet here. It will be floating above this. It will be floating in the air. It will be levitated. Why? Because the permanent magnet, the superconductors will not allow any magnetic field to come in. So this superconductor will become a magnet of opposite polarity. So it will push it up. So it will be like floating in the air. Probably must have seen this demonstration. Yeah, maybe at least as a video. Okay, so we have come to the last slide, I think. Let me see. Yeah. Now it is time to do question. Okay, we have 1 more hour to go. Let me open. I have already posted the homework for chapter 7. Okay, can you hear me now?
Yes, doctor.
All right, so something happened. Okay, anyway, I was telling, we finished the slides, chapter 17. Now it is time to do review to see whether we can apply in solving questions from what we learned. Okay, let me increase the font size. Question number 1. A typical lightning bolt lasts for 0.192 seconds and transfer 1.07 10 to the power 20 electrons, a total charge. So you're being helped by giving you part of the answer. Calculate the average current in the lightning bolt. So the lightning bolt, lightning, it can deliver huge amount of charge. Okay, so he's saying, okay, there was a lightning and that lightning transfers that much of electrons. It's like 10 to the power 20. That is a huge amount of electrons. Okay, and 10 to the power 20. And it lasts for only a small fraction of a second, 0.192 second, fortunately. Otherwise, it will be a disaster if you keep coming like that. It is actual data, okay? It is not just imagining. So in a lightning bolt, you can have a huge amount of charge coming into the earth. You know what is lightning made up of? The clouds get charged and they get discharged to the ground or another cloud. That's where you get the lightning. The question is to find the current. Now, how do you do this? How do you get the current? Anyone want to answer this question? What is the definition of the current? Again, I asked this before.
Can we say the whole question?
I'm sorry, pardon? Say it again.
Can
Say,
you can say the whole question?
you can read it. It is in the screen. I read it now. Are you looking at the screen? Please,
Okay,
if you're listening, you should be eyes open and ears open, both. It's not just you are listening to me only. I have opened this the exam and I'm reading it. I mean, you are supposed to look at the screen as well, not just listening to me. Read it and tell me how to do that. I don't want you to do, at least tell me what is the equation you should use here. We have the charge, amount of charge, and the time.
Q over T.
Yeah, the definition of current, right? Because the lightning bolt supplies a huge amount of charge that gets discharged to the earth or another cloud, okay, from the cloud. So that is what lightning is. The cloud gets charged hugely and it has become so much saturated, it has to discharge. So it can discharge to another cloud or in the earth. It will dump everything to the earth. That is what lightning. So we got the charge because the number of electrons are given. Number of electrons, but it is not Coulomb, right? You have to convert it into Coulomb. So, 1 electron is 1.6 to the minus 19 Coulomb. So you multiply
by
the total number of electrons by that, it will give you the total Coulomb. Again, it's being helped there in the parentheses, you are showing, yeah. So, okay, so you got the charge, then you divide by the time. So let me now look at the solution.
It's not 89.6.
Okay, good. So it is being done. Okay, 89.2. So here the substitution is shown, so you can follow it. Right, let's go to the next question. In a certain material, there is 8 Coulomb of positive charges per second flowing to the right and 8 Coulomb of negative charges per second flowing to the left through a surface. What is the net current through this surface? How do we do this? Hind, can you tell me? We have learned something about, when a charge flow, that constitute current, right? But the charge can be either positive or negative. Then we have the convention. We say if a positive charge flows, the direction of the current is the same as the direction of the charge. Whenever a negative charge flows, the direction of the current is opposite. It has to be in a different direction to the current of the positive charge. Okay, because if there are simultaneously we have positive charges and the negative charges are flowing, the current going to cancel each other, right? And because if positive charges, say 2 positive charges, say 2 protons flows to the right and 2 electron flows to the left, you can say there is no net current because they are going to cancel each other. Proton and electron has the same amount of charge, only the sign is different. So if you have 2 protons going to the right and 2 electrons going to the left, the total current has to be 0. Do you understand what I'm saying?
Yes, doctor.
Very good. Yeah. So that's get the idea, the concept. Okay. So that's why we need to define the direction of the current. The convention is when a positive charge is flowing, the direction is the same as the direction of the charges, the positive current, the charges. But if a negative charges are flowing, the direction of the current is opposite. So when you add One is, when the positive, negative, we will have an algebraic addition. So we can take care of the opposite direction, canceling, and so on. So that's why, okay, this question tests your understanding on that. So here we are saying 8 coulomb of positive charges flowing to the right. So we will say the current from the positive charges, let me call it I1 from the positive charges, is we will choose the sign plus for the positive right direction, okay? Plus 8 coulomb per second, right? Mean that is 8 amperes. Coulomb per second is amperes, right? So the current is 8 amperes, and since it is going to the right, I'm going to choose the right direction as the positive direction, so plus 8. Is that clear?
Yes.
Okay, now let's read the second statement. And we have 8 coulomb of negative charges flowing to the left through the same surface. Okay, what is the net current? So if I call that current due to the negative charges as I2, it is flowing to the left, right? But it is negative charges. So the direction of the current will be also to the right. It's also 8 coulombs per second. So I1 is plus 8, I2 is also plus 8. So the total current is plus 8 equal to
16.
plus 16. That means the direction is to the right. Is that clear? Since we got a plus answer, the direction is to the right. I hope you all followed what's happening here. Maha? Yeah, okay, good. How do I cancel these things? It's going to take all my time. Oh, okay, probably there is a way. Yeah, there is a way here. Oops, what did I do? I closed the whole thing. How did I minimize it? Okay, good. Right, next question. Question number 3. 325 kilometer long high voltage transmission line. Okay, I'm in the next. Hind, are you talking about this one or the previous one? Hind? This one, okay. We are going to do it now. Okay, right. You are talking about this one, right? The currently what I am looking at. Okay. 225 kilometer long high voltage transmission line, 2.15 centimeter in diameter, carries a steady current of 1610 amperes. If the conductor is copper with a free charge density of 8.4 10 to the power 28 electrons per cubic meter. So this is the density of the charge carriers. See, because you forgot about what you learned this equation. We have a relationship between current and the drift speed VD, because we say current is rate of flow of charges, and the rate of flow of charges can be related to the drift speed of the charge carriers and the charge density of the charge carriers and charge of one charge carrier and the cross-sectional area through which the charges are flowing. Okay, it's a matter of simply you forgot about that concept. That's why it confused you. So here it's a matter of just substitution, nothing else. But when you read the question, you should know what equation is relevant there. Okay, if you don't get that, then it's a problem. That's because you did not concentrate. You did not take that concept seriously. The concept of relating the current to the drift speed. Okay, right now you know. Are you okay, Hind? It's fine.
Oh yes, thank you.
All right. Okay. So We got a 325 kilometer long wire. Probably we don't even need this length, which is 2.15 diameter centimeters, and carries a steady current. A current I is flowing through this, which is 1610 ampere. If the conductor is copper with a free charge density, so the N for this charge density is given to us, 8.4 10 to the power 28. What is the average drift speed? So he's asking for VD. So if you know what is the drift speed, then you should remember the drift speed is related to the current through this equation. So if you look at this equation, the only thing that is not known is drift speed. Everything else is given in this question. Current is given, N is given. Q is the charge of a charge carrier. What is the charge carrier in a conductor, metallic conductor? Electrons. Okay, the charge carrier, the charge density is given for those mobile charge carrier, which is the electron. So what you should substitute for Q, which is not apparent in this. Yeah, but anyway, it is given in the parenthesis here. So you put that Q. And area, there's a cross section through which the current is flowing. Wire is like a cylinder, right? Thin cylinder. The cross sectional area of a wire is a circle. So cross sectional area of a circle is given by pi r squared. R is not given, but the diameter is given. So it is diameter divided by 2 will be R. So it's a matter of substitution. Okay, Hind, are we okay now? Please answer me. Very good. Thank you, Hind. What about the others? Is that question clear?
Yes, doctor, it's clear.
Very good. Thank you. So let's go to next question. Let me clear this link. Number 4, when you flip the switch to turn on a light, the delay before the light turns on is determined by, you know this answer, right? It's one of the concepts that we were discussing while we started. Well, you know, we saw that in the simulation, you don't need the electrons from the battery to make a complete journey back to the battery for the lights to turn on. What is needed is the electric field to reach the electron that is already in the bulb. So what is determined? The speed of the electric field, okay? So the answer is D. Speed of the electric field is speed of light, okay? 300 million meters per second. That is quite almost like instantaneous, a huge speed. That's the fastest speed possible. Number 5, when you measure a 20 volt potential difference across 8 ohm resistor. What is the current flowing through it? So Ohm's law. We have a resistor and the potential difference across this resistor is given and the resistance is given. So you can find the
Just
current.
apply.
Just apply. Very good. So this is the simplest question perhaps. So direct substitution, you know what equation to apply. Of course, we will not tell you apply this equation, then it is not physics. It's just a high school math. Okay, if I tell you, okay, this is the equation, this is the number, find it. You don't need to just take a calculator and do it. You are not even doing it manually. Okay, so you just want to see whether you know the physics concepts. I went too fast. Oops. Come on, stop. Which question was that? Where did I stop? Okay, let me use the mouse. Okay, we use this one, Ohm's law. Number 6, the unit of electric current, ampere, is equivalent to which of the following? Okay, so if you apply the Ohm's law, I think this is the only one. It's volts per ohm, so this is not. This is for resistivity. It has nothing to do with the Coulomb. Well, well, this is the one. It's actually volts per ohm. That is originally what its SI unit is. Okay, then we have the ampere. It's also is no. The definition is actually it is Coulomb per second, right? It's delta Q over T. The original unit is Coulomb per second, but it is not there. Coulomb per second is not there. So that is correct. Out of all these is coming from the connection of the current between the potential and the resistance, the Ohm's law. A certain laboratory experiment requires, now this is on resistivity, aluminum wire of length, wire length of 28 meter and resistance of 3.5 ohm at 20 degrees Celsius. What diameter wire must be used? So here resistivity is given at that particular temperature, because at 20 degrees Celsius, and the length is given and the resistance is given. And the question is, what is its diameter? Diameter is connected to the area because wires are cylinders. The cross-sectional area of a cylinder is a circle. So the area of cross-section is given by in terms of its radius. Well, you can write it in terms of its diameter, like this. Okay. Is that correct? Yeah. So now we see that I can get the answer, what is the diameter, knowing this equation for the resistivity. This can be written as, so if you look at this equation, R is equal to rho L. We have R, we have rho, we have L, we have pi, and for our constant, the only unknown in that equation is the diameter. So substitute everything in SI unit and you will get the diameter in meters, right? Is that clear, everyone? See, so just substitution, okay? Again, as I told you, if I tell you what equation to use, it's not a physics problem. It is just someone in the high school can do it. Even you have a calculator, it is about whether you know how to use your calculator or not. Okay, not high school. Someone in grade 5 should be able to do it if he knows how to use the calculator. So you should read the question and you should be able to apply the concepts you learned to the problem. Okay. Next. Oh, it is not being shown. Okay. Anyway, now you know how to do it, right? What is the question? Yeah, I don't know why this is the wrong equation. I mean, not wrong, but it is not done correctly. It is not done for some reason. But you know now, right, how to do it. So it's a good. So it's a challenge for you to do it on your own. This has nothing to do there. Question 8. A wire 2 meters long and 0.25 time. 0.25 millimeters squared in cross-sectional area has a resistance of 40.5 ohm at 20 degrees Celsius. If its resistance increases to 43.0 ohms at 30 degrees Celsius, what is the temperature coefficient of resistivity? See, the formulas are given in the formula sheet. But if you are not already familiar with them, at least try some effort to, look at it and try to memorize it, but you don't have to. Okay, but you look at the equation for a while and just think about it for some time. Then when you see it in the formula sheet, you know which equation to pick for that particular question. Now, this one is talking about the temperature variation of the resistance. The resistance changes with temperature. So that is one of the sections, the whole topic on it. So the equation that was given is this. This is with resistance. It's also given in terms of resistivity, the same equation, but just replacing the resistance with the resistivity. Here in this question, we are talking about resistances, not resistivity. So you get this equation. 2 meter long. Okay. Well, it is not even needed, right? It's a length. This equation doesn't have anything to do with the length. You might sometime be given extra data which is not even needed, okay, to solve the question. Okay, this is area. Do we need that? We also don't need it. Resistance 40.5 ohm at 20 degrees. So this is the resistance, the reference resistance. The 20 degrees is the reference temperature. Oops. Oh, sorry. Okay, right. And this is the temperature that we are interested in. T is equal to 30 degrees and resistance is, so it is increasing to 43 from 40.5 at 20 degrees to 43 at 30 degrees. So that means we are given these values, find alpha. You see, okay, all this information, 2 meters long, cross-sectional area is not needed to do this question. So that really checks you. It is not you're blindly trying to pick the numbers and put into some equation that is there. No, you can't do that, okay? So then you find the value. And again, you should know how to use your calculator without making any mistakes. Okay, is that all clear for everyone? Shall I move to the next? Any
Yes,
questions?
I got it. Yes.
Very good. What about others? Amina, thank you. What about others? Abdullah? Clear. Maha? Hind?
Yes, clear.
Clear. Thank you. Haya, thank you. Some more people, please. Anyone else listening other than Aisha? Okay, thank you. More, Hala, thank you. More people. You're supposed to be 24 people here. Okay, minus one, me, 23 people. Faisal, thank you. More, please. All right. Okay, I'm becoming too greedy now. Let me happy with that many. Right, so let me go to the next. Number 9, the potential difference across a resting neuron in human body is about, even us, the human body has current and voltage, you know that, right? Yeah, because suppose, if you have some problem, some people have heart problem or whatever, they do what is called electrocardiogram, ECG. That is actually measuring the electricity in your body. So even human body has electricity. The potential difference across a resting neuron in human body is about, but it's very small, in millivolt, 82 millivolt, in 0.00082 volt. Carries a current of about, even this is in milliamperes, okay, 0.34. How much power does the neuron release? So you now remember the equation for power is I delta V. Okay, but sometime, we can also, by substituting the Ohm's law, we can also see it is also equal to I squared over R. And it is eliminating the potential. If you're eliminating the current, it will be I is equal to, okay, if you eliminate the current, I is equal to IR delta V over R. So it will be delta V squared over R. Okay, so this equation has no potential difference in it. This equation has no current in it. But anyway, now here we have current and the delta V. So you just substitute, find the answer, done. Simple. Number 10. The 650 watt heater carries a current of 4 amperes. How much does it cost to operate the heater for 40 minutes if electrical energy costs 4 halalas per kilowatt hour? See, now we can see why we introduced this new unit for measuring energy. Instead of joule, I use kilowatt hour, because 1 kilowatt hour, which is 3.6 million joule, cost only 4 halalas, not even 1 real. Okay. Well, I mean, I don't know actual price. Okay, I'm just putting some numbers there. I hope, it's close enough. Now we need to find how much, if we use appliance heater, which has a power rating of 650 watt, we use it, and the current, when we use it, the current is 4 amperes, and we use it for 40 minutes. And how much you should pay? So we need to know how much energy we consumed when I do that. So how do I do this question? We need to find how much energy we consume. So this is the equation. The equation for power is E over delta T. So the energy will be power multiplied by the time. So the power is 650 in SI unit. Okay. So you put the time also in SI unit, you'll get the energy in SI unit, joule. So time is not in SI unit here, in minutes. So you need to convert the minute into second. Now you get this in joule now. Okay, so let me follow the solution now. So you need enough information about the concept. Okay, right. Oh, okay. Right. This is good. Okay, good that I looked at the solution. Now I don't want to get the energy in joule. I like to get the energy in kilowatt hour. You know why, right? Do you? Because the price is given in kilowatt hour.
Kilowatt.
Yeah, the question is to find the price, how much I should pay. So the rate is given in 4 halalas per kilowatt hour. So I'm going to convert the watt into kilowatt, not to don't keep it in watt, but I will. So if 650 watt will be 0.65 kilowatt, and I'm going to convert the minute into hour. So you divide by 60 to make the minute into hour. So I get the energy in kilowatt hour. That's what I need. Now I can go and say the cost will be, because 1 kilowatt is 4 halala. So 0.433 kilowatt hour is how many halalas? That's it. We're going to pay the electricity board only 1.7 halala, not even real. Okay. Okay, let me, oops. Yeah, I think I covered, because like midterm 1, midterm 2 also has just 2 chapters. Chapter 17, which we just finished, and 10 questions from chapter 17, and another 10 questions from chapter 18. So we completed 10 questions. So I will stop the review now. Any question, please?
Doctor,
Yep.
we will have a new homework today.
You will, sorry, pardon?
You will have an we will have a new homework today, and we'll assign
New
homework.
homework? New
Yes,
homework?
for chapters A,
Yeah,
for
I already
chapters 18.
posted. I already posted. Yeah.
Oh,
Chapter
thank you.
17 homework is posted in Web Assign. Please check. Okay. That's one thing. I have another announcement also. Uh, those people who couldn't do the midterm one, okay, midterm one because of the exposure to COVID, some people, I am going to give the exam for them next week, Wednesday. I don't remember the exact date. I will send an email to them, okay, separately. That is one thing. What is the other thing I want to tell? Yeah, please do the homework, okay? Thank you very much.
Thank you, Doctor.
See you
Have a
in the
good day.
next class. You're welcome. Go have a good day.